Hello, 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 and welcome back to another episode of Kerbal Space Programming. Kevin here, and today we are going to be working on our docking script, which we created in the previous episode. So you may remember, in the previous episode, we came up with this translate function, which takes a vector, which you remember is a direction, and then sets the RCS controls to the right parts of that vector so that we can translate in a particular direction. We just give this function an arrow, a vector, and it'll go ahead and figure out the correct RCS controls to set to get us moving in that direction. Now, there was one issue that we encountered with our rather hackneyed docking script, and that had to do with setting our vector to vector normalized. Now, if you remember from the previous episode, setting normalized to a vector makes its length 1, which is what we want to do. If we want to say I want to go in that direction and I want to go very, very far in that direction, well, then we end up with values that are much higher than 1 or -1, and the controls need to be bounded between -1 and 1. So what we had done is we said, okay, whatever the direction is that we want to go, we want to shrink down that vector to a normalized version of the vector, and that way we won't be going more than 1. But there is a problem, and that is that what if it's less than 1? What if we say I want to go only a tiny bit in this direction? So I've gone ahead and updated this function to say only if the vector's magnitude, that is its length, is greater than 1 should we actually normalize the vector. That way if we put in a vector that's 0.100, it's not going to go ahead and say, oh well, I'll expand that to 100. But if we pass in 200, then it will go ahead and shrink it down to 1, which is just what we want. Now, I've also gone ahead and added a couple of small helper functions here because we're going to go ahead and run this test, and I've cleaned up because we had a bunch of code that was just sort of inline, messy. I've gone ahead and written a function that gets our target port, and this is, just for our testing. This is not something that would go in a library, but we're listing the targets, we're getting the docking port length, and we are grabbing the ship that has the docking port B. Now, this is stuff that we just had inline before. And I've also written another function called reset for test, and this is just so that we can go ahead and undock and get some distance from the ship that we're docking to before we start trying to test our docking again. So we're going to get the first docking port and call undock on it. We're going to turn on our RCS, and we're just going to fire for 2 seconds away from the thing, and then we're going to set the thing to off, and then we're going to wait 10 seconds. That way we'll have gained some distance and we can start doing our stuff. So now this is all exactly the same as what we had in the previous episode in our test script. We're going to cancel a relative velocity, which, remember, we're going to take our velocity and subtract the target port's ship's velocity. And then we're going to say until that relative velocity is 0, we're going to translate in the opposite direction of the velocity that we have. So if we're moving away from the ship, then we want to start moving toward the ship until it is roughly 0. And then I've got this, translate 000, which basically just turns off our RCS. We're going to align for docking. We're going to lock our steering to the opposite of the port-facing vector, the vector that points out of the target docking port. And then we're going to go ahead and dock. So what we did there is we said we're going to lock our docking vector to the node position of the 2 ports. So we basically just draw a vector from the target port, from the other way, from our docking port to the target port, and then we've got a vector, which is, however far away and whatever direction those 2 things are. And then we're going to say until our docking port state is ready, or is not equal to ready, which means that it's docked or something, we'll go ahead and translate in that direction. We're going to say in that direction, we're going to normalize it, and then we're going to subtract out the speed that we're currently going. And then we should be done, and we should be docked. So now that we've gone ahead and made this very, very tiny change, the only real change to what we're doing is up here in the top where we change that vector magnitude thing so that we're not firing always with a thrust of total to 1. Now we're going to go ahead and test this and see what happens. And here we are back with our ship in orbit that we tested earlier. And you may remember the last time we staged and then tried to dock. But now, since we were already docked, we undocked. And I'm just going to, set the target port so we can watch the distance. And it fired for 2 seconds, put us in the opposite direction. And now we are canceling that relative velocity. And all right, we are making our approach. And now remember the last time, because we had automatically scaled up the translate to a magnitude of 1, we saw that it was jittering back and forth all the time. But now we see that our target velocity is 1 approximately, and we're approaching pretty reasonably. right? And we're not having to, because we're not overshooting and then trying to backtrack, which is what was going on at the end of the previous episode. Obviously, that was because we were, kind of just making a very crude attempt so that we could get something running with our translate script. But we can see now, as we look at the target, that it is rotating a little bit, and we are approaching at a very weird angle. Now, we're making a straight line path, but because it is rotating as we're doing that, because it does not have any stabilization of its own, it is, not the best. And we're also keeping our steering aligned at the right point. So we're getting close, but there we go. Okay, so it docked, but there's still some tweaks we can make. So let's jump back over to script world. Alrighty, so we're going to make some incremental changes and try and get this script into something that is more workable. For one thing, there's an awful lot of coding here that is messy and procedural, and it would be nice to clean that up into functions, but we'll get to that. The first thing that I want to try and correct, though, is that our thing is rotating, right? And because we are saying go in a straight line toward that docking port, we end up potentially in trouble if it rotates too fast for us to get there in time, and we can end up kind of straddling the thing and spinning around it rather than actually docking. So what I'm going to do instead, remember before we said lock docking vector to target port node position minus docking port node position, I'm going to add something to that. Because we're just basically just adding these directions, adding these vectors on top of each other to say, here's the place where I want to go. So I'm going to add the target port's facing vector, so directly out from the target docking port, and then I'm going to multiply that by 10. So what I'm saying is that where I want to go is actually 10 meters out in front of the docking port. And I'm going to set a start time to time seconds, and then we'll dock as normal. We'll say until docking port state isn't ready, we'll go ahead and translate, but once the time seconds minus start is greater than 120 seconds, so we're going to do this for 2 minutes, then we'll notify that we're actually docking, and we'll lock our docking vector to the original that we had. So first, for the first 120 seconds, we say the direction that I want to be going in is not toward the port exactly, but 10 meters away from the port. And then after 120 seconds, then we'll go ahead and say, now my new vector is the port itself. So let's go ahead and see if this manages to handle this rotation for us. And undocking and docking test number 2, we are away, and we're just making very incremental improvements, trying to get this to something that is more usable. We'll set the target so that we can watch on the nav ball how all of this is going, and you can see that, wow, that thing is rotating far more. We're only, we've only been detached for like 15 seconds or so, and it's already rotated maybe 45 degrees. But you can see we are facing the right direction. It's just that the angle of our approach is a little bit different. Now, this is just because when we undock, we introduce some oscillation in the thing, which doesn't have its own stabilization, which is fine. It's fine, and it's something that we're going to have to deal with. Obviously, you could go into time warp and kill out that rotation, but we want to make sure that our docking is resilient to these sorts of changes in case, we were to bump into something and cause a rotation. We wouldn't want the script to get kind of permanently trapped. But you see now, instead of making a beeline approach, drawing a straight line from our docking port to its docking port, we're actually trying to get to 10 meters out in front of it. And I'm a little nervous now that maybe we should have made it a little more, because we're getting pretty close with that solar panel. But okay, we're fine. And there we go. We're getting ourselves out to roughly 10 meters away. And oh, that's weird. It looks like the audio has cut out for whatever reason. But okay, we're getting to very, very close to 10 meters away. And remember, we've set this up to just say, do that for 2 minutes. And then only once that's done, we'll go ahead and do that. And now it's automatically correcting. And you see that now, even though the body continues to rotate, we are keeping ourselves in this position so that we are 10 meters away. And of course, if we were to do that indefinitely, we'd eventually run out of monopropellant. The ships can rotate, but if we're rotating around the object, then we actually have to use monopropellant to keep ourselves in that position. But we've got ourselves into a parking orbit, I guess, relative to the rotating reference frame of the target craft that we're looking to fetch to dock into. And now it's just a question of waiting for that 2 minutes to time out so that we can go ahead and finish making our final approach. And hopefully, now that we're closer, there we go. We've started, and hopefully now you see it's still rotating, but it's able to rotate less than the amount of time that it takes for us to approach. And there we go. We've managed to go ahead and dock. Let's jump back into script world and see what we can improve. Alrighty, so that seemed to work, but there's one problem, and that is that we don't want to just say wait a certain number of seconds, right? Because who knows if we're going to be in the correct location at that point. It could be that we started from miles away, and by the time we get there, we're still nowhere even close, and we just end up kind of back where we were before. So what I'm going to do is instead, I wrote this function called approach port, and it accepts 4 parameters. It accepts the target port, the docking port that we're docking from, the distance, which is the offset that we want to stay away from the thing, and then the speed. So if we imagine the final docking, this distance is going to be 0. We're going to first just say docking port control from, and then we've got a whole bunch of locks here. So let's kind of go through these in turn. The distance offset is what we had calculated in the previous script. We said we're going to take the port facing vector and then multiply it by the distance. So the direction away from the port and then scaled up by however far away we want to stay from it. We're going to set our approach vector to that target port position minus docking port position, so the line between our docking port and its docking port, and then we're going to add the distance offset to that. We're going to lock our relative velocity, that's stuff that we've done before, and then we're going to lock our steering to the opposite of the direction pointing out from the target port. So this is all just sort of repurposing stuff that we had inline before. Now I'm going to do the same thing until docking port state is ready. Now we may not, if we're just saying get to an offset, then that's never going to change. So we're still going to have a separate case to break out of this loop if we're saying, get to 10 meters away from the docking port. But we'll get there. So we're going to translate in the same way that we did before. We're going to take that approach vector, normalize it, multiply it by the speed, and then subtract the amount that we're already going. And now I'm going to say we're going to create a distance vector. And that is just the node position minus the docking port position. That's just the vector between our docking port and the target docking port. And I want to introduce another function, and this comes with KOS, is called VANG. This is vector angle, so the angle between these two vectors. What we're going to check is we're going to say, all right, what is the angle between the direction that our docking port is facing and the distance vector, which is the direction between the vector between our docking port and the target's docking port. So if we imagine if we're facing forward, but the docking port is off to our left, then the angle is going to be a lot. We want the angle to be very, very small. We want to make sure that we're pointing in the same direction as the direction that we want to be going, and then we'll know that, okay, we're reasonably aligned. So we're going to say, if that is less than 2, and the absolute distance, the absolute of the distance minus the distance vector's magnitude. So remember, when we talk about magnitude, we're talking about the length of the vector. So that direction between our docking port and the target's port, we want to figure out what's the distance of that, and we're just going to subtract that from the distance that we wanted to have. So if we were saying approach the port with 10 meter offset, we'd say, okay, well, we're 11 meters away. We'll take 10 minus 11. We'll take the absolute value of that. We'll go, okay, well, it's, that's 1. Once the distance and the distance vector's magnitude are very close to each other, they're less than 0.1, then we know, all right, not only are we aligned, but we're also at approximately the right distance. Well, then we can go ahead and break out of the loop as well. And then we're just going to wait 0.01 in here so that we can continue to do this translate stuff. And then just to clean up, we're going to translate to 000 just to make sure that we turn off our various RCS controls. So I've also gone ahead and moved our kill relative velocity stuff into its own function. We're just giving it the target port, and this is just moving up the stuff that we had inline into a function. So we're just getting that relative velocity, and we're saying until it's less than 0.1, translate in the opposite direction of that velocity, and then turn off the RCS when we're done. So now we can go ahead and clean up our inline stuff. We've got resetting for test and all that, but now this body is much simpler because we say, okay, we're canceling our relative velocity. We'll kill relative velocity. We'll say we'll make a 20 meter approach, and here we say there's the target, there's the port that we're controlling from. We want to be offset by 20. We want to be 20 meters out in front of the port, and let's go ahead and approach it with a speed of 5. And then we'll say make a 10 meter approach. When that is done, we'll approach it with a speed of 2, and then we'll say make our final approach with an offset of 0 and a speed of 0.5 meter per second. So you see now we're starting to get to this point where we could, even if the thing were rotating very, very fast, we could have a whole bunch of these where, approach it at a distance of 5 and 4 and 3 and 2 and 1, and it would not step up to the next one until it knew that it was roughly right in front of, within a 2-degree margin of error, right in front of the target docking port. So let's go ahead and see how this improves our script. And we are undocking again, and I realized in our previous test that we actually dipped barely into the atmosphere. It's fine, we only dipped by a little bit, and we still have plenty of velocity, so we're fine. But that's why the sound cut out that time. But okay, so we're canceling the relative velocity, and now we are making our 20-meter approach. And now that we've abstracted this out into functions, we really don't have to worry about making typos or figuring out these vectors. Every time that we want to do something, we can just call the function. And we see that because that first one we were approaching at a speed of 5, and even now we're approaching at a higher speed, that we are capable of overshooting. But now, as we are making our final approach, we've slowed down to 0.5 meters per second, and we are getting much, much closer. And we could go through and just do these kind of meter by meter if we wanted to, and maybe we'll eventually do that in a function. But okay, we know our function works. Let's get back into scripting. So there's one additional thing that we need to think about when we're looking at docking, and that is that if we want to make this script kind of fully automated, we need to be a little bit careful about how we plan our maneuvers. Because if we are over here and we say we want to get to 100 meters off of the docking port, let me grab a line tool, and we want to get to 100 meters away from that, well, that's fine. We'll first go here, then we'll go, okay, we've gotten there. Of course, it'll be spinning around at that point to align, but it'll go here first, and then it will go here. But let's imagine that we say get to 100 meters or 10 meters away from the docking port, and our starting position is here. Well, then we've got a problem. We're going to try and ram right through the thing before then trying to get to where it should be. That's not so great. So what we really need to think about, especially because once we deal with larger craft, there is sort of a bubble in which if we try and travel through, things are going to be a little bit dangerous. So let's draw like a little safety bubble. We've got a safety bubble. Great. So we've got this sort of safety bubble in which it is dangerous for us to do stuff, right? So, okay, we've got our ship. Let's imagine if we've been both spinning around and we've got our rendezvous. The first thing that we need to be careful of is that when we start our docking script, we don't know exactly where we are. It's possible that there is a solar panel, coming out blocking our way here, that there's some sort of range in which we really, really, really want to be careful that we don't cross. What we want to do is we want to say, for this ship, we really want to only maneuver around kind of outside of this bubble, and then we'll come in once we are exactly aligned. And then we know, okay, if there's a docking port there, there's not going to be stuff in our way if we're moving in sort of a straight line path down into this. So the first thing that we want to do is we want to say, regardless of where we start, let's immediately get ourselves the heck out of here. So the first thing that we want to do is we want to ensure that we get to outside of this bubble. Now we want to get to here, so right in front of the docking port. But obviously if we do something like this, there's a risk that we're going to run into somebody trying to get there. So what we first want to do is we want to say, let's get to the side. Let's get to over there. So the first thing we want to do is we want to get to the side of here. What? Okay, come on. Now you're just, Photoshop. What is your deal? Okay, we want to first get to this side. And only then when we've gotten there, at the same range, then we can go ahead and make a maneuver over here. And this, of course, is assuming that there's some sort of, that we're going to cut into this range a little bit, but we'll assume that, we will set the radius of the danger zone such that this distance is not a problem. So our real maneuver plan, kind of from regardless of where we started, is to go, let me see. Yeah, so let's set this up. So a real maneuver plan, regardless of where we start, is to first get out range, and then we'll go ahead and get to the side of the docking port, and then we'll get to the front of the docking port, and only then can we make our approach. And we can think about this the same, like if we were to start here, we'll do the exact same thing. Now we don't necessarily care what side it is, so immediately get out of range, and then go ahead and get yourself to the side, and then go ahead and get yourself up front and make your way down. And this way we can be reasonably certain that we can dock with our target without running the risk that in the effort to maneuver to the right location, we end up crashing through something that is, delicate. Okay, so now it's docking script number 4, and we're making improvements. We're really getting there, all right? So we've got our approach script, which is great. It's working for us, but we're going to add 2 new methods. One is ensure range, and this is going to take the same types of parameters. We're doing very, very similar to approach. We're setting all of these relative positions and all of these vectors. We're taking the relative position of the ship's position minus the target ship's position. We're getting a depart vector, which is our relative position times the distance minus the relative position, which makes sense, right? We're saying we've got the relative position, so the direction away from the direction from the target ship to our ship. When we want to say scale that down to 1 and then multiply it by the distance, and then subtract however far away we currently are. We're going to set our relative velocity as we've done before, and we're going to lock the steering too, just to make sure that we don't have too much excess RCS that is firing, not accounting for various steering. And now we're just going to translate in the opposite vector, so away from the craft, minus the speed that we're currently going, at the speed that we should be doing that. And then if the departure vector magnitude is less than 1, we'll go ahead and brake. Now here we don't actually have to care about whether or not we are exactly, let's make this 0.1. But we don't have to care about whether we are aligned with the docking port in this case. So in the approach function, we had multiple conditions. We were checking the angle between various things, but here all we care about is that the amount of distance is exactly what we wanted it to be. And there's also one small thing that we can change here, and that is that if you have an if block and it has just a single thing that you want to do, you actually don't need these braces. You can go ahead and get rid of them. So I'm going to go ahead and do that here. We can do that. We can say if depart vector magnitude is almost 0, we'll go ahead and break out of the loop, and then we'll translate to nothing again. Now the last function is sideswipe port, and these are all fairly similar, you see. So we're going to take the same parameters, we're going to do docking port control from, and the other thing that we need to do is we need to find a vector, a direction that is perpendicular to directly pointing out of our target port. Because we want to make do a crisscross to the side before we get ourselves in. If we try and go just directly straight toward 100 meters out from the docking port, well, if we end up behind the docking port to start, then we'll plow right through the ship trying to get there. So we want to veer off at an angle and get back. So I'm going to say, let's assume that the side direction can be the ship's starboard vector. Right? We'll just assume that that's not the same as the port-facing vector. But then just to be safe, we're going to go ahead and take the scalar product of that side direction and the port-facing vector. And that can be 1 or -1 if the directions are the same or exactly opposite, which we don't want. If that's true, then we'll say, okay, well, starboard vector happens to be the same direction that the target is pointed in, so we'll go ahead and change our side direction to the top vector. And one of those two is going to work. And now these locks are exactly the same. The only thing that's different is that our distance offset is now based on a side direction, not the actual direction that we're looking to go. We'll take our approach vector to the same thing, the distance between the 2 docking ports, but then plus that side direction times whatever distance. We'll lock our relative velocity, we'll lock our steering, and then we'll do the same thing as we did with our avoid method. We'll just say wait until that approach vector's magnitude is less than, and yep, we'll do the same thing here, 0.1. So once we've gotten the appropriate distance and we are to the side of the ship, then we know we're not going to hit into it, and then we can go ahead and start our real approach. So we've got the kill velocity, we've got all this, and look at what's happened to our inline body here. And we can actually eventually even make a function that just automatically handles these various steps. We'll ensure the range, so wherever we happen to be, we're going to make sure, okay, we don't want to collide into anything, let's get 100 meters away in the fastest way possible. We'll go ahead and ensure that we are 100 meters away from the thing at a speed of 5. Then we're going to cancel our relative velocity. We're going to make that side swipe maneuver. I'm going to say go 100 meters, but to the side of the ship. Now go ahead and get to 100 meters in front of the docking port and at a speed of 5. Then we'll make a 50 kilometer approach at a speed of 3, a 20 kilometer meter approach. We'll make a 20 meter approach at a speed of 2, a 10 meter approach at a speed of 1, and then we'll make our final docking approach. And I think eventually we'll go ahead and take all of this logic and we can put it into a simple function that says, here is the target port, here is the docking port, do basically exactly this step. And we can wrap that up in one function that just takes the 2 arguments, and then we have got ourselves a docking library. Let's go ahead and see how this runs. So we have done a lot in this episode, which is run rather long, but what we've managed to do is we started off with a very simple function that takes a direction and throws the RCS at it, right? Now what we've done is we've created kind of second order functions that build on top of that function. They use that function and figure out what the appropriate direction is for various things that we want to do. And this means that we could build, third order functions that kind of encapsulate this entire behavior, doing the getting to range, getting to the side, getting to the front of the thing, and then bringing it in for a close approach. We may even, just to sort of automate it, rather than kind of copying and pasting those, approach to 20, approach to 10, approach to, 0, so we could do a countdown. We could just loop over and we could say, set the distance to distance -1 and just do that over and over. And there we go. Okay, so we've gotten to the side, which is great, and now we can make our 100 meter approach, so we're getting ourselves around to 100 meters away. Now, obviously, with this ship, it's not a big deal because there's not much we're going to run into, but, if we imagine that we were docking with our future space stations, well, then we've got to be careful because the craft could be significantly larger. We're getting ourselves up there. Come on, and it's just waiting, really. We're at the right distance. Well, we're close to the right distance. We're just waiting until we get roughly into alignment. And just about there. Come on, get up there. But this is very exciting because now we can pull this into its own library and start actually doing stuff with our docking. Now we still have to go ahead and grab our rendezvous. We've done it in a previous episode, but I think that we can make that a little bit cleaner. We'll go ahead and have to look and steal from previous episodes to do that. But once we've got a rendezvous that puts us within a kilometer or so, this script should theoretically get us to dock because it'll get our approach to 100 meters away, and then it'll start going ahead and getting ourselves in closer and closer. So we've got our 100, and there's some it's rotating around because that darn ship is rotating pretty significantly. We're getting to our 50, and we're moving pretty quickly. And I think we're getting close to the just below the atmosphere, but it'll be fine. It'll be fine. And in fact, this craft is really up here so that we have the ability to test stuff. But okay, so we're making our 20 meter approach, and you can see on the nav ball, you can see we can watch it drifting away from, or it rotating rather, drifting away from the direction that would like it to stay in. But this is good because it means we're not going to collide into stuff, and we can dock confident that we're not going to end up destroying stuff in the process, which is important because there's not really an easy way to detect that or abort that other than, perhaps looking at all of the various parts and trying to track their positions and avoid all that. Right, we are making our final approach, which means that we have a good and functional library that we can use in future episodes for doing more awesome stuff. Okay, come on, stop rotating. And flip it around, for whatever reason. That's fine. But yes, we will start building our space station in the next episode, so I will hope to see you then. Cheers.